Hello, everyone. It's me, Mr. Younger. On Tuesday the 15th, I actually recorded a class with one person in attendance, but come to find out it didn't actually record. So I'm now repeating that class. I'm actually using the same notes we did. I filled them in and I spaced them out so that I could talk you through it as opposed to writing in real time. So let me start off by going ahead and sharing my iPad screen with you guys. All right, so now you're looking at my iPad screen. So I've written down a title called Kirchhoff's Rules because I'm going to introduce the two rules. The first one is the KLR, the Kirchhoff loop rule. It says the sum of all the voltage changes encountered as you imagine a particle following any closed loop in a circuit is equal to zero. Note, resistances represent voltage drops only if your imaginary particle crosses it, i.e. the resistor, in the chosen direction of the current that goes through the resistor. So for instance, when you run into a resistor as you're completing some loop within a circuit, if you're actually moving in the direction of the current in that particular leg, when you actually cross the resistor, then because you're going in the same direction as you hypothesize the current to be going in, then the resistor is a voltage drop. However, if you're going the other way, if you're going the opposite direction of the hypothesized current direction, then the resistor has to be a voltage increase. Additionally, this one doesn't tie in as much with the current and it doesn't tie at all. But when you go from the short arm of a battery, the battery diagram is drawn as two, almost like a capacitor, two capacitor plates, but one's really short and that represents the low voltage end and the other's really long and that represents the high voltage end. So all that matters with those is if you go from the short line towards the long line, then that is a voltage increase equal to the voltage of the battery. If you go from the long line to the short line, then that is a voltage decrease. Again, this case, the voltage decrease is a exactly equal to the voltage of the battery. So that's what this extra note for Kirchhoff's loop rule is showing. Now I will show you what Kirchhoff's junction rule is. Kirchhoff's junction rule. I should say an example will make this a lot rule easier to understand, so you don't feel bad if you don't understand it yet. Anyways, now off to Kirchhoff's junction rule. The Kirchhoff's junction rule is the sum of all the currents entering a junction is equal to the sum of all the currents leaving the junction. A junction is a point in an electric circuit where three or more current carrying wires connect to one another, or with one another. So I'm sort of giving you not only the Kirchhoff junction rule, but also explaining what a junction means. And I will remind you that the KLR statement, the Kirchhoff loop rule, is just a statement of conservation of energy because basically every voltage drop or increase is a change in energy because a volt is the number of joules per coulomb and joules is a unit of energy. So the KLR is just a conservation of energy consequence, and the KJR is a conservation of charge. So you can imagine once you have a particular wire that you imagine a current is moving through it towards a junction, then there's a certain number of charges that enter that junction from that one wire every second. That amount of charge per second is the current. And if you have a certain amount come in but a different amount going out, then you haven't conserved charge. So let's carry on with a couple of drawing examples. So you can imagine, for instance, in this case, you can see not only the junction, but you can see the definition of the junction, which I said was at least three wires passing together are coming together. In this case, I've got two that are entering the junction, the little purple dot, I1 and I2, and then one leaving it. So according to Kirchhoff's junction rule, the sum of the currents entering a junction is equal to the sum of the currents exiting the junction. In this case, I1 and I2 are entering, so I got I1 plus I2 is equal to the only one that's actually leaving is current I3. So it's I1 plus I2 equals I3. Here's another diagram just to make sure you understand entering a junction versus exiting a junction. In this case, you've got I1 entering the junction and only I1. So you have I1 by itself on the left-hand side, but you have I2 and I3 leaving the junction. So you have I1 is equal to I2 plus I3. Or in a more general sense, here's a bigger example. you can see that in this case, I actually have 8 wires converging at this junction. The currents are I1, I2, I4, and I7 entering the junction, and then I3, I5, and I6 and I8 leaving the junction. So that suggests our Kirchhoff's junction rule equation should be I1 plus I2 plus I4 plus I7 is equal to I3 plus I5 plus I6 plus I8. So hopefully that's pretty straightforward for you guys to understand. So let's go ahead and apply this to a particular circuit. And this is a circuit very much like one of the ones that your book has in it. But again, I'm trying to not violate copyright laws, so I change them up as somewhat. In this case, I start off with this circuit, and this circuit has what we call 3 legs. Notice it also has 2 junctions. I've shown the junctions as green dots or green circles. And then the legs are individual single current wires. So you can imagine current I1 is going through the top leg. You can imagine current I3 is going through the middle leg. And then you can imagine current I2 going through the bottom leg of the circuit. So I'm first off going to use the Kirchhoff loop rule for the upper loop. And in this case, what I'm doing with it is I'm starting in the upper loop, but I'm starting right here at this position and I'm going this way. So that's me traversing the circuit in a closed loop. And you can see the first thing I run into is a voltage change due to a battery. But I'm going from this itty bitty short leg to the long leg, so that's a voltage increase, hence I got the plus 55. Now I am going the direction of the current in this leg. The current in this leg is I3, and I've hypothesized I3 to be moving to the left, and I am moving to the left. Since I'm moving to the left, I'm moving the direction of the current, so we expect the 1 ohm resistor, this guy, and the 50 ohm resistor to be voltage drops. So I put 1 times I3 as a subtraction for the 1 ohm resistor and negative 50 times I3 for the second resistor subtraction. Now I get to this junction and I start to go around the top leg. Again, I'm going the same direction as the current I1, so anything I run into should also, as a resistor, should be a voltage drop. And sure enough, using V equals IR, we say 40 is the R and I1 is the current, so I say minus 40 I1. And now I'm back to the same place I started, so I can say equals 0. Now, once we've done that, we need to go ahead and combine like terms, and then I always suggest my students to number their equations because when you have 3 unknowns or 4 unknowns or 5 unknowns, you have to have exactly that same number of equations. Or in principle, you could have more, but more can sometimes make it an unsolvable problem. So it's not necessarily a better thing to have more. So in this case, like I said, we are going to have 3 unknowns, I1, I2, and I3. We want to determine all of those currents. We just found one of the equations, and now I'm going to clean it up and number it. So combining like terms, I get 55.0 volts minus 51.0 I3. That's from me adding the 1.00 ohm or the 1.0 ohm resistor. Uh, and that gave me 51, negative 51 I3, and the 40 I1, it was already there. Now I'm going to do a different loop. So we're going to use the Kirchhoff loop rule again. This time I'm doing the outer loop. And you can see that basically what I'm going to do is I'm first going to go, where did I start? I started where I2 was. So basically I think I'm starting, let's double check. Yeah, I put it in a wrong order. I'm not. It's weird. I'm using the same notes, so I can't remember what I did necessarily. But you can see I must have started going around the circle in a very specific way. This minus 90 suggests that I was going this way, which is the opposite direction of the current. So for some reason, I did I2 before I did 30 I2. But either way, what I was really doing was going in this direction around the loop. And again, it is the outer loop. So that's the loop I'm doing. I should have written plus 30 I2 plus 1 I2, but for some reason I did 1 I2 first and then 30 I2. Notice we are going the opposite direction of I2, so these resistors are voltage increases. That's why I have that plus and that plus. So again, plus 30 I2 plus 1 I2. Then I go from long leg to short leg, so that means it's a voltage drop of negative 90 or a voltage drop of 90, and therefore we put it as a negative in here. And now when I get to this junction, I'm actually going the same direction as the current, so the resistor at that point will be a voltage increase, or excuse me, a voltage decrease. So now I get to it, and that is current I1. So using V equals IR, I'm just multiplying the 40 ohms, which is the R, times the current I1. And since I'm going the direction of current, it's minus 40 I1. Now we need to combine like terms again. Obviously, it's a fairly trivial step, but I showed it anyways. So we ultimately have 31 I2 minus 40 I1 minus 90 equals 0. I'm calling that equation 3. Oh, and I also already did and I don't even know why I missed it. I think I was remembering another example I did, but from the very beginning, we're looking at the leftmost junction, this spot right here, and we can see we have I3 coming in, we have I2 coming out, and we have I1 coming out. So it should be I3, which is the in one, equals I1 plus I2, which are the out ones. So that's why that was equation 1. Sorry I didn't mention that first thing. Now we're up to equation 1 and 2, and now 3 was the last one we just did after we combined like terms. And now our goal is to figure out some way to solve this. By me doing these two loops that had a common wire in it, that actually allows me a technique that almost always works when solving the system of equations. Specifically, the junction rule tells you it combines all the currents basically in this circuit. If you get a more complex circuit, you might have to have multiple junction rules, but in this case, we only have one. If I'd put a junction rule for the other one, it would have been I1 plus I2 equals I3, which is the same equation, just in the opposite order. So anyways, with that in mind, when you go to solve a system like this, if you choose your loops wisely, you will have one loop that's common to both of the equations, and then you'll have, or yeah, one current, excuse me, that's common to both equations. So for instance, by me going through the upper loop, I had I3 and I1 involved, and then me going through the outer loop, I had I2 and I1 involved. So I1 was common to both of them. You can see minus 40 I1, and then you can see minus 40 I1 in equation 3 as well. But in equation 3, you also have I2, and in equation 2, you also have I3. So what we can do is we can solve equation 2 for I3, and it will be I3 in terms of I1. We can solve equation 3 for I2, and it will be in terms of I1. So by doing that, we would actually have two separate equations that relate two separate currents to I1. We can put those currents in equation 1 as we show here, and then we'll only have one unknown and we'll be off to the races. So solve 2 for I3 and 3 for I2, and then plug those into equation 1 because there will then be only one unknown. So that's me just restating it. Now, what I did was I took equation 2, and you can imagine me taking the minus 51 I3 and pulling it to that side. It'll become positive 51 I3. So then you'll get 55 minus 40I in the numerator, and then all we have to do is divide by 51 to get rid of the coefficient, and that gives us I3. Now, this isn't the nicest way to plug I3 into equation 1. I've found it works really nice if you break this up into two separate fractions, 55.0 divided by 51.0 minus 40.0 divided by 51.0 times I1. if you do that, you just want to make sure you keep at least one, but preferably two or more extra digits beyond the sig figs, so that you won't round it so much that your result bears no resemblance to anybody else's. So I've gotten I3 explained here, the solving of it for I3. I've got it explained here, but now I'm going to use the calculator to divide 55.0 by 51 and then to divide 40 by 51. And that gives me this result, 55.0 over 51. That was 3 sig figs divided by 3 sig figs, which gave us 1.0784. You can see the 8 and the 4 extra digits that I kept. Similarly, 40 divided by 51 has also 3 sig figs, so it's 0.784, and I kept the 2 extra digits 3, 1. So we're now calling this equation I3, which equals 1.0784 minus 0.78431 I1. We're calling that equation 2 prime because it really was equation 2. We've just solved it for a different variable. Now I'm going to do the same thing with equation 3. And you can see that in this case, when I'm solving for an equation 3, when I'm solving for I2, I could leave I2, the 31 I2 on this side, and I could pull the 90 over here. It'll become positive. I could pull the minus 40 I1 over to there. That'll become positive as well. So I'll get 90 plus 40 I1, and then all I have to do is divide by the coefficient of I2, and that would be the 31.0. Again, we're going to break this up into fractions, 90 over 31.0 plus 40 over 31.0 times I1. And again, I'm going to carry a couple extra digits. When I do that, this is what I got. 2.9032 with the extra digits is 90 divided by 31. And 1.2903 is 40 divided by 31. When adding 2 extra digits, and we call that equation 3, again, because it is equation 3, it's just solved for a specific variable. So now that we have that, we see we have I2 in terms of I1, and we have I3 in terms of I1. That allows us to put I3 in this slot and I2 in this slot, and we'll have some function of I1, some function of I1, and I1 all in it, and therefore we have one unknown in one equation, and we can immediately solve for I1. So when I plug those in, as I tell here, you're going to plug 2 prime and 3 prime into 1. When I plug them in, I get this part for I3 and this part for I2. So you can see it's just this equation came right down here, and this equation came right down here, and this is the I1 that already existed. So now you can see that I have basically I1 in one term on the left and I1 in 2 terms on the right. In fact, the 2 terms on the right are positive, and they're going to add up to be 2.29. So when I pull this term over to this side, that's going to become even bigger, an even bigger positive coefficient of I1, and I'll subtract 2.9032 from both sides, and that'll put all the numbers on the left and all the I1 terms on the right, in fact, as 1. So when I do that math, I end up getting negative 1.8248. Notice I carried 2 extra digits still. These, remember, when you're adding or subtracting, the significant digit rules are a little more complicated. You have to figure out which particular addend or subtrahend or whichever part you're doing with the addition or subtraction, you have to figure out to how many decimal places are those figures significant. And the one with the least number of decimal places that are significant dictates the answer. So I've got to be careful about that. In this case, I added 1.0784 and negative 2.9032. Both of those are good to 2 decimal places, so I can round the result to 2 decimal places. That's why it's negative 1.82, and then 4 and 8 are not significant. Similarly, when I added the 1.290 to the 1, and then I added another 0.784, that should have given me 3.07. And again, in that case, we had 0.784 was good to 3 decimal places. The 1 we can assume is good to any number. The 2.9032 was only good to two decimal places, so that allows us two decimal places in the coefficient of I1 being significant. So that's why I have 3.07, and then I have the 4, the 6, and the 1 underlined. Now all I have to do is divide both sides by 3.07461, and that gives me I1 is equal to negative 0.59351 amps. So the negative tells us that we were incorrect when we actually guessed the direction of I1 being to the right through the 40 ohm resistor. We actually got that wrong. That's okay. I don't want my students shouldn't waste any time, at least during a test, trying to figure out exactly whether I1 goes to the left or right when they're making their diagram to show and label the currents, because really the picture is all you necessarily have to be given. You don't have to be given any of the currents or their names or anything like that, or their directions. So you normally have to choose the names of the currents and the directions of the currents, and you're completely free to do that. When you're doing it in a homework setting and stuff like that, it's very good for you to try to predict and think about the circuit to see which way the current's going to move or go. And then when you're done with it, if you find out it's wrong, you can go back and try to figure out your logic, where your logic went wrong. That'll help you in the long run better understand how circuits behave. But during a test, you just want to throw the answer down there. And also, even during homework, you don't want to waste a lot of time doing trying to guess exactly what it is, because at the end of the day you want the answer to the solution to the problem, and the answer to the problem just requires you to choose any direction for all three, and then make your equations, or for all the currents, and then make your equations consistent with that. So now that we do have I1 and we found out that it's negative, we do know that I1 was going the opposite way, but we still got to keep that negative in all the equations we made, because all that negative resulted from the fact that we had chosen correctly. But all the equations that we wrote, equation 1, equation 2, equation 3, equation 2 prime, and equation 3 prime, were all based on that current going that direction. I1 going to the right through the 40 ohm resistor, I3 going to the left through the 1 and the 50 ohm resistor, and I3 going to the right through the 1 and 30 ohm resistor. All of those were based on, or all of those facts is how we got the equation. So now when we go back to plug I1 in, we have to use it as a negative number and include the negative. So going to the next part, we can now use, for instance, equation 2 prime. If we plug I1 in that, that'll give us I3. And if we take equation 3 prime and plug I2 in that, or excuse me, and plug I1 in that, we'll get I2. So that's what I'm doing here. I went ahead and plugged the current for I1 in the expression for I2, which is the 3 prime. So I'm using 3 prime, and this right here is 3 prime. So I'm using 3 prime, which says 3 prime says that I2 is equal to 2.9032 plus 1.2903 times I1. Now, when you go to do this in computation, you really need to first do this multiplication, because the multiplication that happens right here is contingent upon the fact that I only have 3 sig figs times 3 sig figs. So the answer will come out to 3 sig figs. And when you do that, you've got to then see exactly what decimal place you need to round it off to, because next you're getting ready to add based on where that round off was. Okay, remember the addition and subtraction is always a little more complicated, because you have to round it to the number of decimal places that the number that had the fewest decimal places had. So if you don't know exactly which decimal place these non-sig figs begin in after this multiplication, then you won't get the significant figures right. So in this case, what we discovered was the significant digits after multiplying 1.290 times negative 0.59351, that resulted in a product that was 3 sig figs long, and that product, in fact, was 1.2903 times 0.59351, 0.63551, not worrying about signs, I'm just worrying about the multiplication. When I multiplied that, that gave me 0.765805. So knowing that it's 3 sig figs, that means I get 3 decimal places total. So the term down here at the bottom, or excuse me, the term down here at the bottom where I multiply these two quantities together, they actually gave me precision all the way to the 3rd decimal place. But this one only gave me the 2nd decimal place. So when I add those two numbers, the product of these two and this, I have to round it to 2 decimal places, and that's why I've got 2.13 as the appropriate sig figs. But the next digits 7 and 4 are not significant, and in fact, you'd have to round this to 2.14 technically. Now that I've found I2 and it came out positive, we know our I2 direction was correct, but we also know that our I2 current was 2.14 amps. Now we can also take I1 and plug it into the equation for I3, which is 2 prime. So that's what we're going to do here is I3 is 1.0784 minus 0.78431 times I1. But again, we have to carry out this multiplication first because we see we have 3 sig figs times 3 sig figs. And when we do that multiplication, again, let's try it, 0.78431 times 0.59351. When I multiply those two, I know I'm supposed to get 3 sig figs out because both of them had 3 sig figs, and the answer is 0.46549. That means 3 decimal places are good again. So I have 3 decimal places good from this term, but I only have 2 decimal places are significant from this term. So I have to round the result to 2 decimal places, and therefore my result is 1.5439, where the 3 and the 9 are not significant. But now I have completely solved the system of equations, and I can now state all of the currents. I1 is equal to 0.593 594 amps, and it's obviously going in the opposite direction as we labeled. I2 is 2.14 amps, and I3 is 1.54 amps. Now that we've done that one, I can go on to another example. And in this one, this is not unlike the one in your book where your author is having you consider what happens when you actually connect two batteries to jump a car. So that's what we're looking at here. You can imagine the top leg as basically a jumper cable and another jumper cable, and then this is the strong battery that's doing the jumping. This is the weak battery with its internal resistance, just like the strong battery had an internal resistance. But this is the weak battery in this leg. And then this leg is actually just the wire that comes from the battery to the starter and then goes back from the starter back to the black terminal of the battery or possibly to the chassis. Okay. So in this part, we're asked what current can the weak battery deliver by itself? In other words, let's pretend like this whole leg here is not there at all and just pay attention to what's left of the circuit. When we do that, we'll get the current that the weak battery was giving. Then in part B, it says what can the starter receive while jumping? In other words, now we're going to work it out with that other battery connected and see if we can find that it gives a better current. So we begin. First off, whoa, this was not the solution I meant to jump to. Oh, okay, that one's it. So first off, that was jumping way too far ahead. The solution is going to involve us using the Kirchoff junction rule, which we call KJR, the Kirchoff loop rule, which we call KLR, and Ohm's law, V equals IR. Remember, that's what all those terms are in Kirchoff's loop rule. So first off, we're going to attack just that lower circuit. So you're ignoring this top leg with the 0.11 ohm resistors and the 0.010 and the 12.5 battery. We're ignoring all that wire. And what we see is we just have a power source with two resistors in series. Those resistors are 0.13 ohms, which is the starter motor's apparent resistance, or the starter's apparent resistance, and the 0.030 is the internal resistance of the bad battery. So we add those two and we get 0.160 ohms. That's only good to 2 decimal places. Now, because in fact we had three decimal places with the 0.030, but we only had two in the 0.13. So that's how we had to make it 0.160 with the zero not being significant. Now we can use Ohm's law, V equals IR, to say 10 volts is equal to the current times the total resistance, 0.16 ohms. When I do that, I get 10.0 volts divided by 0.160 should give me the current, and that current turns out to be 62.5 amps. Notice how we had 3 sig figs divided by 2 sig figs, so that ended up us only allowing us 2 sig figs. So we're only getting about 63 amps here. Now we can do the whole circuit again using the Kirchhoff's rules and V equals IR. So we first attack the outer loop, and the outer loop, what we're going to do is we're going to imagine that we start up here at this point and go down. Let me double check that first. Oh, no, actually, it's a little weird how we have it drawn, but I'm going to do the outer loop from this junction right here all the way around this way like that. That's the way I'm traversing it in this Kirchhoff's loop rule equation. So first off, I go with the direction of the current I3. So that means this resistor, and this resistor are all voltage drops. So I get negative 0.11 times I3 for this jumper cable. I get negative 0.010 times I3 for that internal resistance. And then I get negative 0.11 I3 for that third resistance, that other jumper cable. And of course, in between that, I went from the short side of the battery to the long side. That meant my voltage was an increase, so I got the 12.5 there. And then I'm still going the direction of current in this bottom leg, so the starter motor has a resistance that'll be a voltage drop, and that voltage drop is given by I times R, where R is 0.13 and ohms and I is I2. So now we have completed the entire loop, so the equation should be equal to zero. That's what we got. We can combine like terms, and that gives us this equation. So you can see all I did was take the three terms, which is that one, and that one. Notice I checked them too. That's a good way to keep track of what you have done and what you haven't done. So when I added all these, as I added them, I'd write a check mark. So 0.11 plus 0.010, that gives me 0.12 plus, and again, they're all negative. That's why I said plus. Plus 0.11 again, that gives me 0.023. So that's why I got that. Then I have plus 12.5. Because there's no common terms for that one, and minus 0.13 I2 because there's no other common terms for that one either. And you see that now equation 1 is our Kirchhoff loop rule for the outer loop. Now we're going to choose another loop and do another Kirchhoff loop rule. This time we're doing the lower loop, and the lower loop is actually going to be starting here, going around this way. So notice I am going the right direction, I2, that the current I2 is, and I'm going the same direction as the current I1 is, so the resistors will be voltage drops. Since I'm starting here, the first resistor I want run into is 0.13, and that has a voltage drop given by I times R, where R is 0.13 and I is I2. So that's why we have minus 0.13 I2, and then we go minus 0.030 I1, and then we go from short leg to long leg, so that's a plus 10 volts, 10.0 volts. So that's equation 2 for our Kirchhoff loop rule. Now all we have to do is make a Kirchhoff junction rule because we have three unknowns, I1, I2, and I3. And we need, of course, three equations. We've only got two so far. So the junction rule for this junction right here sees that I3 is coming in and I1 is coming in and only I2 is going out. So our junction rule should be I3 plus I1 equals I2, or probably I would write it as I1 plus I3 equals I2. And lo and behold, we can get that. Actually, I hadn't added that yet, but anyways, what we're starting to do now is, since we're going to have that Kirchhoff's junction rule that I said was I3 plus I1 equals I2, we're going to do it just like we did the last one, where we're going to solve for the common current that we have in the two equations, which you can see equation 1 has I3 and I2, and equation 2 has I2 and I1. So what we want to do is, since both of them have I2, we want to solve this one for I3, and we want to solve this equation for I2, or excuse me, this equation for I1, because then they'll both be in terms of I2, and we can put them in the loop rule. So let's do that. You can see that I've taken equation 2, and I am now trying to uh, actually, no, I'm taking equation 1, and I'm not trying to solve that for I3. So if I pulled negative 0.23 I3 to the other side, it would become positive 0.23 I3, and then I'd have 12.5 minus 0.13 I2. That's exactly what I have here. And then I have to divide by positive 0.23, the coefficient of I3, to solve for I3. Then, using a calculator, I'll compute this fraction and this fraction, or as basically as a division problem, and that gives me 54.348 minus 0.5652 times I2. That gives me a equation for I3 in terms of I2. Now we can take equation 2 and solve that for I1 in terms of I2. When we do that, we're going to get I1, which had a coefficient of negative 0.030. So if I pull it over here, it becomes positive 0.030 I1. And then I have 10 minus 0.13 I2, just like that. And then I just have to divide it by the coefficient, which is 0.030. So again, I'm going to divide 10 by 0.030 to get one term, and then I'm going to take the I2 term by taking 0.13 and dividing it by 0.030. When I do that, I get 333.3 minus 4.333. Now, again, this was 2 sig figs divided by, or 3 sig figs divided by 2 sig figs, so I only had 2 sig figs, which meant it was only good to the tens place. The tens, T-E-N-S, not T-E-N-T-H-S. Similarly, when I take the 0.13, which has 2 sig figs, and divide it by 0.03, which has 2 sig figs, the answer comes out to 2 sig figs, and it turns out to be 4.3, and only the 4 and the 3 here are significant. These 3's are not, just like these 3's are not. But now I have an equation for I1 in terms of I2, that's called 2 prime, and an equation for I3 in terms of I2, and that's called 1 prime. Now all I need is my Kirchhoff junction rule, which I already told you is I3 plus I1 is equal to I2. So with I3 plus I1 is equal to I2, which I swore I'd already written on here somewhere, but obviously I did not. But what we've done is we've actually implemented that in this case right here. So what I've done, even though it doesn't show it in these notes, is I took equation, let's call this equation 3, and that equation 3 was Kirchhoff's junction rule, and that was I1 plus I3 is equal to I2, and that's Kirchhoff's junction rule. So if I take the I1 that I found from equation 2 prime and put it in this spot right here, then I would get specifically 333.3 minus 4.3333 times I2, duh, exactly what I have, plus I3, which was 54.348 minus 0.5652 I2. And you can see that's exactly what I have here, 54.348 minus 0.5652 I2. And then that's all equal to I2, which is the last term. So that's what I've done there. I don't know how I didn't write it before, but I apologize for not putting that in that until now. But now we have clearly one equation that has combined equation 1, equation 2, and equation 3 all together. This is all from equation 1, equation 2, and equation 3. So we've already combined all those, and we now have exactly one unknown, and that's I2. So my plan here would be to bring this I2 over to here. It'll become positive, and I already got 1 there, so that'd be 1 plus 0.5652. And then I also going to bring this one over there, and that's 4.3 added to it. And when we do that addition, it turns out to be specifically uh, right here, we can see we get 5.8982 I2. And then the other terms, the 333 and the 54.348, stay on the other side, and we get 387.648. Again, whenever you're doing these multiplications and then additions, you've got to check the number of sig figs that come out of the multiplication before you can figure out how many sig figs are left after the addition or subtraction. So I did do that. Ultimately, I was able to get all the I2s on the right with a coefficient of 5.8. 982. Obviously, the 9, the 8, and the 2 not being significant. And then the combining of the like terms for the constant terms was 387.648. So now I just got to divide 387.648 by 5.8982. When I did that, I got I2 is equal to 65.72 amps. And if we look at our circuit, that I2 is what goes through the actual starter. So what went through the starter is a little bit bigger. 62.5 amps was what we got without the jumper battery. But what we got after the jumping battery was there was 65.72. So we went up by about 3 amps roughly. Not a huge amount, but maybe it's enough. Who knows? Now all we have to do, even though the circuit just really asked for the current through there, or the problem just asked for the current through the starter engine, but why would we waste time and solve this whole circuit without finding out what the other currents are? So I'm now plugging this I2 into my expression for I3 that I got in equation 1 prime, and I'm then plugging in what I got for I2 in my equation 2 prime for I1. And again, I have to multiply this part first, realizing it's 2 sig figs times 2 sig figs, and figure out where the decimal place comes out at. In this case, it could have been, well, actually, let me just check it out. It's 0.5652 times 65.72. That's 2 sig figs times 2 sig figs gave me 37.14, 1449. But since it's only good to 2 sig figs, the fact that the number was 37.14 tells us it's only good to the ones place. What's worse is the 54.38 was also only good to the ones place. So I shouldn't say what's worse. It's just basically the same thing. So we can only express this to the ones place, and in fact it's going to be 54 minus 37, which is how we get the 17.20 without the 2 or the 0 being significant. Similarly, when we take 4.333, which is only good to 2 sig figs, and multiply it by 65.72, which is also only good to 2 sig figs, that case we get 284.7648, but it's 284 and we only have 2 sig figs, so it's only good to the tens place. Not only that, the 30 the 333.3 is also only good to the tens place. So no matter what, we only technically have the significant digits to the tens place. And that literally forces us to only have one sig fig, which is really horrible. That's part of the reason why I don't require my students to use sig fig rules except during lab. But even then, I try to use propagation of error for better results. Or at least I've taught them that they should use propagation of error formulas for better results. All right, so that's it. We've done that circuit as well. We've got the currents are 65.72, 17.20, with, of course, the proper rounding, and basically 5 times 10 to the 1 amps for I1 if we stuck to our sig fig rules. Now, since we've done that, we can go ahead and start along with the next bit of material. And the next bit of material that we're covering is RC circuits. This is not RC like radio controlled or remote control that you're used to. This is RC, meaning circuits that involve resistors and capacitors and a power source. So what we do is we're imagining, in this case, a specific circuit that has a battery. This right here is a EMF source. That's why they're using this. You can either treat this as a like a cursive E or an epsilon or something like that. It doesn't really matter too much. The main thing is the English alphabet's not quite big enough. Even when we include the English alphabet and the Greek alphabet, we still run out of symbols. So we just have to use what we use. We're saying here's a hypothetical circuit. We have a power source, an ideal battery that has a voltage, which we also call electromotive force, even though that's sort of a misnomer. We have it as a voltage equal to E, so we can pretend like we actually know E, we can pretend like we actually know C, and we can pretend like we actually know R, and we're going to work with those variables as if they're known quantities. Okay. What's going to happen here is this battery is connected through a switch. That's what this is, the switch. And when we close the switch, the circuit is completed. And what happens is this side of the battery is the positive side, and that's a high voltage thing. The long side of a battery is always the high voltage end, and we picture it, even though it's not the reality, we picture loose positive charges sitting around in the wires just waiting to be motivated to go somewhere. So when I connect this battery through to this wire and then close the switch so that the particles have a way to not only leave from the battery but to return back in the negative side of the battery, then what happens is the positive voltage on the top side of the battery plate, i.e. the positive side of the battery, that compels all the free positive charges to move around, 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 and they start to build up on the plate at the top of the capacitor. As they start to build up on the top plate of the capacitor, they compel the free charges in the bottom plate and the wires after the bottom plate to run away. So the positive charges now are running through this resistor and then trying to come back to the negative terminal of the battery. That's going to continue until the voltage across this battery, across this capacitor, is exactly equal to the voltage across the battery. At that point, there's just as much compulsion or just as much ability to push the positive charges from the top side of the capacitor to the battery as there are to push the positive charges from the top side of the battery to the top side of the capacitor. That's why equilibrium has been established once you get the capacitance having the same voltage across it as the battery has. Remembering, of course, C is equal to Q over V, you can see that the V would actually be equal to Q divided by C. So that would allow you to determine the voltage, or if you wanted to determine the current, or excuse me, the charge, the C equals Q over V just becomes Q is equal to CV. So if you multiply E times C, you will get the total charge that the capacitor has in it across it when it's reached equilibrium. So we know from this description of how it works, we know what to expect. In other words, what's the voltage across the battery going to look like? Well, the voltage across the battery is initially going to be or excuse me, what's the voltage across the capacitor going to be? Well, we know the voltage across the capacitor before the battery was ever connected was just sort of zero, but we know over time it's going to slowly approach, and I suspect it's going to asymptotically approach the voltage of the battery. So if we think about the graph of this, we can look at the next page and you'd see what we expect is the voltage starting from zero to rise, 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 but it's going to asymptotically approach the voltage being equal to the voltage of the battery. In fact, if it obeys the typical exponential curve, we expect that the time constant, RC, will be the amount of time that passes in before it goes from 0 volts to 63% of the asymptotic value. Not only that, you can say that that's also how the charge on the capacitor is going to behave. You can actually say this graph also represents the charge across the capacitor, but instead of E, it would be C times E that it's asymptotically approaching. So now I've gotten both V and Q written on the same graph. And I also started to realize, or I started to draw the graph for the current, because what you might realize is this capacitor is literally an open circuit. That's what a capacitor does to a DC circuit. It just makes it not a circuit at all. There's no way to do it, and in some sense, there's no way current can flow across that gap. That didn't happen. Nothing that I told you suggested that currents actually jumped from the positive plate. Individual charges did not jump from the positive plate to the negative plate. That is not necessary for what happened. But the equivalent of that happened just by the positive plate stacking, or excuse me, the top plate having the positive charges stack up on top of it. As they stacked up, they compelled the positive charges that were free in the bottom plate to run away. So it's equivalent to a current flowing across there, even though no current actually jumped the gap. Okay. But with that in mind, we imagine that the current, no matter how it's done, did start as having a value as if it was just a battery connected to a resistor, so that V is equal to I times R. But over time, that current is going to decrease because you're going to build up charge, build up charge, build up charge. Specifically, the current is going to be negative dq dt because the current only comes, not in this case, scratch that. In this case, the current is going to be dq dt, not the negative dq dt. I was thinking of the discharging part. But while we're charging it, the current is the derivative of the charge with respect to time. So we expect that exponential decay for the current, but we expect exponential growth asymptotically for the voltage and the charge. Therefore, just with those graphs in my head, I can immediately write out exactly what the equations will be. Your book did take the time, and you can find it also on my YouTube channel in various videos. Your book took the time to create Kirchhoff's loop rule for this circuit and then converted it to a differential equation, and then they solved that differential equation to get these solutions. You ideally would be able to, as a student, to figure out how to do that and be able to do that in the future, but that is really a high standard that I would like students to strive for, but I don't expect them to get it. So all you have to do for me in this class is you have to be able to use those equations that are derived. Again, we're just using Kirchhoff's loop rule, which you can sort of picture if you really wanted to go around the loop this way. You can say, okay, well, V is equal to IR. That's one equation, but we also know V is equal to Q over C. So if we talk about Kirchhoff's loop rule, then our loop rule, if we start from, for instance, right below the battery, and go this way, what we would find is E is a voltage increase because we went from the short leg, the negative terminal of the battery, to the long leg. So that's a voltage increase plus. Now it's going to be a voltage drop from the fact that the wire that connects the top plate of the battery is going to all be at the same voltage as the top plate of the battery. So if the battery, for instance, was 12 volts, then this whole piece of wire here would all be at 12 volts, including this top plate. So with that in mind, we know there's a voltage drop of E from here to here in some sense, right? But I said of E, but I mean of the electromotive force. There's a drop of the electromotive force in going from this side to this side. So that drop, according to, again, C equals Q over V implies V is equal to Q over C. So we're going to say this is minus 1 over C times Q. And I wrote Q to the side for a reason that'll become clear in a second. Now I'm also going further past the capacitor to the resistor this way. I'm going the direction of the current, so that resistor should be a voltage drop, and the voltage drop, of course, is R times I. Now, now I'm using R times I as the voltage drop, but I've gotten back to the same point in the circuit where we begun. So we can now write the equation as equals 0. But now I'm going to plug in the fact that I is equal to dq dt, and I'm going to solve it basically, or show you its differential equation by solving it for E, and it'll be E minus, or excuse me, E equals Q of T times 1 over C plus R times dq dt. So that's the differential equation that came from Kirchhoff's loop rule. And like I said, your book does go about solving that. I'm not requiring you to do it, but I am requiring you to use the results, and here the results are. So we've got Q is equal to C times E times parentheses 1 minus e to the negative t over RC, and we call that quantity RC. You should be able to verify this. This is definitely a low-hanging fruit that every instructor teaching this class expects of you. You should be able, at the drop of a hat, to show definitively that ohms times farads gives you units of seconds. Okay. Once you know that, then you can see RC is a time constant, and it's just C times E times parentheses 1 minus e to the negative t over RC, close parentheses, and the voltage would look exactly the same way, except we know that voltage is gotten by taking the Q and dividing by C. Remember, C equals Q over V gave us that V is equal to Q over C. So if I take this quantity Q that I just told you is the solution, if I divided that by C, then I'd get exactly this expression, and that's why these two graphs look alike. Now, if I took the derivative of Q, now that we have Q, like that, if I took the derivative of that with respect to time, this first term, C times E times 1, is going to be 0. The second term is going to be negative. Derivative of e to the negative t over RC is just e to the negative t over RC times the derivative of negative t over RC, and the derivative of negative t over RC is negative 1 over RC. So the negative times a negative gives a positive, and we get CE times e to the negative t over RC. That's the entirety of the current. Now that we have that, we can specify that this specifically really is the equations, but only the equations for actually charging the capacitor. So I'd say charging the capacitor. Okay, so those are equations for charging. Uh, in this case, I don't know why this is here, but I think I'm just about done. But I got to show you one example, and I also want to show you the discharging equations, which are a lot easier to deal with. So ignore this page for right now. In fact, I'm going to move this page to the trash because I don't need it. And you can see now I'm back to where I started from with the charging equation as well. There's charging the capacitor. This is much more useful. Now, in discharging the capacitor, we can see that discharging the capacitor, what you're imagining here is we have this circuit with just a charged capacitor and a resistor. but no battery, because that's sort of the whole point. Is a capacitor acts like a battery whose energy withdrawal can be controlled. In other words, you can set how fast you want the energy to be withdrawn from that capacitor, whereas you can't do that with a battery. It's pretty much just going to pull it out at its own pace. So a capacitor is better in that sense. But what we're going to see here is as soon as you close that switch, then the positive side of the capacitor is going to just act just like the positive side of a battery, and it's going to compel all the free charges that are positive to move around the circuit this way and to come back here. Now, as that happens, they're losing a little bit of energy because they're going through a resistance R. And again, you can write Kirchhoff's loop rule for this. And in this case, you'd basically get that the voltage across the capacitor minus I times R is equal to zero. You can turn that into a differential equation, and slowly you can solve the differential equation and get the equations for the current, which is basically the current in the circuit, the charge on the capacitor, which we call QC often, and the voltage across the capacitor, which we call VC. Now, we do expect all of them to just exponentially decay, because initially what you have is a good amount of voltage. Specifically, you're going to have a voltage V0 that, if it happened to be the same circuit that we were dealing with before, we know exactly what the V0 is. In fact, the V0 would have been exactly equal to the EMF that we used to charge it up with. So if we had used a 12-volt battery in the previous part of charging the capacitor, then the voltage for this capacitor would start off at 12 volts, and we'd call that V0, and we expect it to exponentially decay, as we see from this graph. Uh, Also, the charge Q is equal to C times V. So if I just took C and multiplied it by the V equation, I'd get Q, and that's why these two equations look so similar. Now, in this case, as I accidentally hinted at before, uh, every bit of charge on the capacitor, as it leaves, it becomes current. So we're actually losing charge on the capacitor at the expense, or at the expense of the capacitor, we're creating current. So in that case, we're going to say I is not dQdt, but I is negative dQdt. And sure enough, you get this third equation. And that really is it. That's the discharge in the capacitor. I thought I had worked another example uh, for that, but I do not see it here, so I must not have. And that's okay, because this is plenty long of a tutorial or a lecture anyways. So I'm going to leave it at that, and later on today or tomorrow, I'll make a video showing charging a capacitor example, showing discharging a capacitor example. We are skipping the section on electric health hazards, though you should read it and you should know that stuff. I'm just not going to test you on it. And we are going to do, even though I told you I probably won't test you on it, I am going to do the creating a voltmeter or an ammeter out of a galvanometer. So I'll show you some of those examples as well. But that's it for now. Thank you for coming, and I hope you all got some understanding of that, and I apologize for it taking an extra 2 days. Have a good one. Bye-bye.